Any other questions on this one? Take a linear algebra class and learn how to do Gaussian reduction by hand with matrices. At least by hand, it'll go a lot faster that way. What? That last part, I can't hear that last. Yeah, when you add them together, it should come out to be 15. Yeah, it's rounded. It's rounded, yes. Yeah, if I was just trying to keep 3 total significant figures here. But yeah, I guess it would be, what, 1556 or something like that? Yeah. Yes, Bill. Yes. 8/9 is going to be, if you use the fraction mode on your calculator, 8 divided by 9. Yes. Awesome. Any other questions on this one? I can show the QR code for one more second. No problem. Whew. All right. All right, so for the circuit shown in figure 2568, the capacitor is a 6 microfarad capacitor. The EMF is 100 volts, and R is 500 ohm. After having been in contact with A for a long time, the switch throw is rotated to contact B. So one of the things that is being said here that maybe you pick up on or you haven't picked up on is when the circuit is closed, so when you have this right here, the circuit being closed, then what that means is that the current is allowed to flow around to this plate, and so you end up getting all of the positive charge collecting on this plate right here and having negative charge being drawn from that plate down here on the bottom side. And it says that it's sitting there for a long time. We said that when a EMF, or when a RC circuit is charging, then the amount of charge is going to be equal to, just trying to think off the top of my head, it's equal to EC times 1 minus e to the minus t over tau. Trying to pull that off the top of my head. Somebody tell me if I'm wrong on that one. But I think that should be the charge as a function of time. And if time is very, very long, so we're going to assume that time is infinity here. And if we take e raised to the minus infinity, then this term is going to go away, and we just get that the charge is exactly what we would expect the charge to be if the RC circuit had no resistor in it, right? It has had enough time to fully charge, is another way to say this. And fully charged would be, in this case, 100 times a capacitance of 6 times 10 to the minus 6 farads, and that's going to be equal to 6 times 10 to the minus 5 coulombs, or that's 60 microcoulombs. 60, oh, no, sorry, it wasn't 10, it was 100, so that would be 10 to the minus 4 here. And that means that we've got 600 microcoulombs of charge. 600 microcoulombs sitting on this capacitor. What is the current? Well, actually, let me stop and say here, because this is a common mistake. What happens, before we get to part B, what happens when the switch is in between contacts A and B? What takes place? Let's say that instead of jumping straight into B, the problem said A part 2, the switch is then rotated between the two contacts and is left there for a long time. Bill? Okay, so that is the number one answer that I get when we've got both of the switch between A and B, where it's not contacting either one. But the problem is an open circuit does not allow charge to flow. So it does not discharge while the switch is open, meaning that it's not contacting A nor B. So it sits at A to charge up, and then I rotate it between the two throws. Nothing happens. I mean, assuming this is in a vacuum and there's no humidity in the air to draw off charge from the capacitor plate, like this is an isolated system. But while the switch is here between A and B, no charge can flow because the circuit is broken. Right? I mean, it's the reason that the lights don't come on inside of your house if your switch is broken. You go and turn on the switch and your lights don't come on, assuming the power isn't out. Well, it means that the mechanism inside your light switch in the wall is broken, and it can never close that circuit to allow current to flow.
So if it's broken like that, it just means the current can't flow, but it's not necessarily discharged, that the charges are still just...
Yeah, it's just sitting there. It's just sitting there, yeah. In fact, I didn't do this on, on Thursday or Tuesday of last week. I don't remember when it was. But if you go to FET, I think they might have one for RC circuits. And so you can play with exactly this, but I don't think they do have resistors in there. So let's look at this one. But I can't draw this one up. Let's do this a different way, okay? Let's do the FET current lab. So if you go to the FET current lab, you can set up multiple branches with several different EMF and the like. So this is going to be my EMF here, and I'm going to do it with conventional current showing. And what you can do is you can have a switch just like the one that we had before. I'm going to have to think about how to do this. Let's see here. I'm going to put a switch here and a switch here. I'm going to have to think about how these are each flowing. And then I put a resistor here. So I'm not going to have the capacitor, but I think this will at least give you a little bit of an idea of what's going on. I'm going to put a wire here and a wire here, and I'm going to drop the last wire from here to here. So more or less the same way that this system was set up, right? And I could set my system to be closed where I get current flowing around this direction. But as soon as I have, this would be akin to both of them being open, I don't get any current flowing, right? I don't think there are any capacitors in here. I can even switch to this, so that way we get an idea of what it would look like. But yeah, I don't get any, I don't have any capacitors in here. It would be mighty nice if I did. If I close this switch, then my EMF catches on fire because there's zero resistance here. I've shorted out the circuit. But what it's trying to, let me break this one here really quickly. Now, in the case where I throw my switch to B, then I would have, if there was some sort of capacitor here to allow energy to drain off, Or you could think of that capacitor as soon as the switch is closed as being an additional battery but going the opposite direction. Then you get this while the switch is closed, but you get nothing while that switch is open. Not necessarily an asymptote, but certainly discontinuous, yes. Yeah. There's a break. There's nowhere for the charge to flow, right? As soon as, what you could think of as a capacitor that's charged, think of it as a really short-lived battery. That's all it is. So you close the switch here to B, and once you've closed the switch to B, then the capacitor will start draining off charge opposite the direction that it was previously flowing across that resistor. But instead of it being able to maintain that EMF, what's going to happen is it's going to drop off in voltage very, very quickly. In fact, exponentially quickly in terms of its drop off. And so now it's discharging to where the current is going to eventually stop and go to no current at all. That's what happens when you close the switch to B. But while the switch is open, while it's in this configuration, nothing can flow, so nothing happens. We've charged it up by throwing it to A, we break the circuit, the charge just sits there. And then we come along in part B, and we throw the switch closed to B. And now, exactly what I just showed will happen. You're going to get current flowing along this direction. Right? And it says, what is the current just after the switch throw is rotated to contact B? Well, for a discharging circuit, we said part B is the current is equal to I naught times E raised to the minus T over tau. I don't think I wrote it up here before, but tau, don't forget, is equal to RC. Resistance times capacitance is the time constant. And what is the current just after the switch throw is rotated? So just after is trying to tell you that T is equal to 0 here. That would be I naught, sorry. So when T is equal to 0, the exponential is not 0, it's 1. And so we get the current is equal to I naught. And on the slides that I showed you last time, we said that I naught is equal to V naught, the initial voltage across the capacitor, divided by the resistance R. Yes, Maggie. Yes, if there were multiple resistors, you would have to follow the rules of adding the resistors in series and parallel. Yes. Jacob? Say that again? No, because I was doing a long time, T goes to infinity. And the exponential of minus infinity is 0. Yeah, so up here, I had T equals or goes to infinity. Here I've got T equals 0. So this is only valid when it is charging. As soon as I switch to the discharge state, then I have to switch to a new set of variables, a new set of conditions. And in this case, I'm restarting the clock at 0. So my question is, what is the initial voltage across the capacitor? I hope that wasn't someone's brain frying. What is the initial voltage across the capacitor? 100 volts, yes, it is. because the capacitor is fully charged. So we get 100 volts divided by a resistance of 500 ohms. That means we get a 200 milliamp current, right? Here's the rub. On your homework, what will happen, or on an exam, what will happen is part A will say that we close the switch to A, and it stays that way for 1 second, meaning that the capacitor does not fully charge, right? It doesn't reach the maximum amount of charge, the 600 microcoulombs. Let's say it only reaches 300 microcoulombs in that 1 second. I don't know what the actual number is, but it only gets halfway charged or some partial way charged. How then would you calculate what the voltage across the capacitor is if part A said we only partially charged the capacitor? It would. Your V and your V here would have to, it would not be equal to 100 volts if you hadn't fully charged the capacitor. But how do you calculate the specific value? Because part B and C and D don't change. Yes, we know the definition of capacitance is equal to Q over V. That was from our first unit, right? And so if you know how much the capacitor was charged in part A, then divide by the capacitance, and that gets you the voltage across the capacitor, right? If it only charged halfway, well, this is a linear relationship, then that means that I would have only gotten to the point where I have 50 volts out of 100 across the capacitor. If it had charged to 400 microcoulombs, then I would have gotten 66 volts, 66.7 volts charged, and so on and so forth. But it's only when it's fully charged do I get the same potential across the capacitor that I had across the EMF to begin with. Part C, going back to where we went to fully charged. What is the time constant of the circuit? Well, we said that time constant is equal to RC. So that's going to be 500 times, 6 times 10 to the minus 6 farads. That comes out to be 3 times 10 to the minus 3 seconds, or that's 3 milliseconds. Yes, in part B, irrespective of what irrespective of how long part A takes, whatever the charge was at part A is going to be the initial charge at part B. And so we could calculate that the initial voltage across the capacitor in part B is going to be equal to the charge that we got in part A. So that's 600 times 10 to the minus 6 divided by the capacitance of 6 times 10 to the minus 6. Well, that's 100, right? So that's the 100 volts that I used there in part B, right here. Good. Oh, man. How do ohms what is it? Ohm farads. How do ohm farads come out to be seconds? There's always one, man. Ohms, if V is equal to IR, right, then that means that R is equal to V over I. And if I take the units of that, that means I get volts per amp, right? But a volt is equal to, let's see, a kilogram meters squared per second squared per coulomb, and amps are coulombs per second, right? So that means that I get coulombs cancel. I get one factor of per seconds canceled. So I've got now kilograms meters squared per second. But then I've also got farads, and farads are charge over volts. And if I take the units of those, then I get coulombs per kilogram meters squared per second squared per coulomb. As well, I still get coulombs and, no, I guess that would be per coulombs and per coulombs. So I would actually have coulombs squared here. I would end up having, well, you can see where the volts are going to cancel out maybe, and where if the volts cancel out, let's do it that way. R is equal to V over I times capacitance, which is Q over V. That's the easier way to do it, rather than going back to SI. My volts are going to cancel out, and I is equal to Q over time, right? So I've got that, and then 1 divided by time gives me time. So that's where seconds comes from. That took me a lot longer to get there than it should have, but should have been prepared for that question. Okay, part D. How much charge is on the upper plate of the capacitor 6 milliseconds after the switch is thrown? Well, we said last time that Q is equal to Q naught, which, since it's fully charged, or whatever we got in part A, that's going to be the 600 microcoulombs we got in part A, times E raised to the minus T over tau. And the reason in part B that they had you solve for the time constant, 6 milliseconds divided by 3 milliseconds, that's just going to be equal to 2. 6 divided by 3 is 2. So we get 600 times 10 to the minus 6 coulombs times E raised to the minus 2. And this comes out to be equal to 81.2 microcoulombs. Pardon? Tau is TAU. Yeah. Like alpha, beta, tau, or whatever. I don't know. Tau is the time constant. It's a characteristic of time, right? So let's think about what tau means physically. And that's why I wrote it out this way with E raised to the minus 2. And remember, when you raise a number to a negative exponent, it's like taking 1 divided by that number that many times. So 2 times here. So what tau tells us is, for this circuit, every 3 milliseconds, you take your initial value and you divide it by E. So after 3 milliseconds, you take 600 divided by E. So 2.7. After 3 more milliseconds, so 6 milliseconds total, you divide by E again. And after 9 milliseconds, you divide by E again. And so you're just taking a division by E, 2.71, every 3 milliseconds. Not necessarily come back around. It's generally, if you look at the physical way to think about it is, after you've divided by tau twice, it comes out to be about 67 or 0.67%. So after 2 time constants, you've lost about 67% of what you're using. After 3 time constants, you get to 90%. And after 4, you get to 99%. So within 12 milliseconds of the switch being close to B, which has taken us longer to solve this problem than 12 milliseconds, right? So very, very quickly, within 12 milliseconds, you've lost 99% of your charge. Okay. Any other questions here? All right. Let's switch gears then and go into our slides for today. I don't know if y'all are fans of Whose Line Is It Anyway, but the inspiration of this question, if you've ever watched Whose Line, they do it where usually Colin is playing some figure and he's doing an interview, but he doesn't know who he is. And based on the questions that it gets asked of him, he has to figure out who he is. And usually the first question that Ryan asks is, why? And Colin's typical response is, well, I'm going to have to give you my typical response and say because. And then they move on from there. But I'm a fan of Whose Line Is It Anyway? The British Whose Line Is It Anyway and the Drew Carey one. I haven't watched a lot of the new stuff. I like Colin and Ryan together. Like anytime Colin and Ryan are doing something together, it's comedic genius in many ways. Okay, so today we are ready to dive into new material. Take everything that you have learned about electricity so far and rotate it by 90 degrees, which just makes it a lot more complicated. And you've got magnetism, like in a nutshell. And I'll tell you guys what I told my last class. We're going to talk about the magnetic force today on currents and on charges. If a particle is moving one direction and the magnetic field is going another direction, then the force that it experiences is in a third direction. It's a cross product. Weirdly enough, it feels like, since we know that the electric field pushes on charges, and when the electric field pushes on charges, the charge moves in the direction that it is pushed. It's weird to most students, and it's still weird to myself to think about magnetism, because that means that the charge is going this way and I push on it in any given direction, it all of a sudden just makes a right-hand turn and does something completely different. Like Monty Python. Now for something completely different. Right? And if you want a good explanation of this, before I even go into the mathematical details of it, and I know you already watched the video on it, the pre-lectures, but before we go into any of that, there are 2 or 3 great videos, one by 3 Blue 1 Brown, one by Minute Physics, and then one by, I think, Veritasium, that goes into using relativistic physics, why you get weird results of directions of force on charges as they move through magnetic fields. Because when you look at relativity, magnetic fields are just Lorentz transformed electric fields, or at least that's one way to think about it. But I'll send those out in a video and or in an announcement on Canvas. Last year, I got really excited to find those videos, and I felt like I'd done a really good job as a professor. In the next class, I asked how many people watched the video, and out of the class of 60, 0 had watched it, and I was super disappointed going out of my way as a professor. All right, yeah, so let's get to this slide. Magnets experience an electromagnetic attraction. Opposite poles attract while like repel in a similar fashion to charges. The big difference in Maggie's question here is my statement about magnetic poles only come in pairs, meaning there is no magnetic monopole. It means that, as far as we can tell and we have ever measured, and there are still physicists out there trying to disprove this statement, but as far as we have ever measured, if you have a north pole of a magnet somewhere, you better have attached to it a south pole as well. You never get a north without a south, or a south without a north. And the monopoles, what monopoles mean is, if I could switch gears here and go back to what I've got, our notebook here, our class notebook. What this would look like if there were magnetic monopoles, it means that you could have little north charges by themselves that pushed out a magnetic field, and you could have a magnetic south pole, wrong way, that did something like this, and in that case, they would more or less behave the same way as charges, right? But that's not what happens. You only ever get something that looks like this, where you get a north here and a south here. That's all that ever happens. So, jumping ahead to Thursday, what does the nature of a magnetic field look like that is different from, it always loops back in on itself. Magnetic field lines always loop back in on themselves. What you get is something like this right here, where you get the magnetic field looping in on itself, where it goes out of the north pole of the magnet and into the south pole of the magnet. And this, confusingly, is how a lot of your textbooks tend to draw a bar magnet the first time you ever see it. And what I just stated here with this is that magnetic field lines never have a start or stopping point. If the statement of no magnetic monopoles is true, meaning that this right here is invalid. And so then your book, after making that statement, shows you this image right here. And one observant student in every class always comes up and says, I thought you said that magnetic field lines don't have starting and stopping points. And you look at the image and it's like, look, professor, it starts right here on the north end of the magnet and it ends right here on the south magnet. It breaks the rule that you just told me magnetic fields follow. And I said, yes, that's a poor graphic representation of what's going on. Because what's missing from this? What's missing is that the magnetic field line goes all the way through the bar magnet, like this. And it does make one or sets of complete loops. So do not be deceived. Do not be deceived. And as a matter of fact, this comes up so often, I might just make it an exam question. I'll throw one of those graphics on there, and you tell me what's wrong with it, multiple choice style.
Well, if magnetic fields they don't have a start and stop, how do you get rid of them? Like, how do they, like, you know, they don't,
You blow really hard. I don't know. No, just kidding.
like,
Where do they come from?
or where do they go?
Where do they go? That's a good question. So here's one of the more frustrating things, right? Because your first time through a modern physics class, what they'll tell you is, okay, there exists in the world little things called electrons, right? And that electron is going to have a magnetic moment that looks something like this. Right? Well, the semi-classical way to explain it is it's because electrons have spin. Right? So electrons have spin, and it's a charged particle, and what we're going to talk about is fundamentally where magnetic fields come from is they come from moving charged particles. We're jumping ahead to like Tuesday of next week, but it's a good question, right? So moving charged particles make magnetic fields. But here's the rub. According to quantum mechanics, this electron has zero size. It is a point in space. And points don't rotate. So classical idea of spin, that you take the basketball and you twirl it on your finger, and that's what the electron's doing, that goes away. Okay, so what happens? Like, where does this come from? Well, just like charge, it seems that angular momentum and therefore magnetic moments of charges is just a fundamental property of nature. And that's the best I know to explain at this point and at this level. But it's a fundamental property of charged particles down on the atomic scale.
So they don't spin, but everything around them spins?
No, not even that. It's just like charge. Where does the charge come from, right? Well, charge is, choose your grand unification theory or string theory or M theory or whatever you want. Like, ultimately, charge is just like mass, is just a fundamental property of matter. So is magnetism. So is angular momentum. Good questions. I guess actually I drew this magnetic moment going the wrong direction. Since it's negative charge, it should have been going down, but that's okay. Doesn't mean anything anyway. Okay, no magnetic monopoles. Good question, Maggie. As with electric charges, there exists a magnetic field B that is associated with the magnetic strength and direction surrounding magnetic materials and electric currents. And in general, you could use something like a compass to measure the direction. A compass which just has a magnetic material in it, or one that responds strongly to magnetic fields. And the North Pole is going to align to the direction that the magnetic field points. And right now, we'll get to the question that was asked after Maggie's question. We'll get to where magnetic fields come from. But all I need you to know right now on this slide is magnetic fields exist. And we're going to talk about the consequence of them existing, how magnetic fields interact with matter. And then we'll come back to how matter creates or generates magnetic fields in a little bit. So here's something that's interesting, is you go to the surface of you arrive on the surface of the earth as if for some reason you had left. So this is Earth rotating on its axis, right? Like so. And you, as a person, are going to get dropped at this point right here on the equator. Right? We'll call this the equator. So you're on the equator, and you have a little compass, and the needle points this direction, which means that the local magnetic field, at least in your region on this lone blue marble in space, at least per Carl Sagan, is going to look something like this. And then it's going to terminate here and come out of the planet like so. You end up getting something that looks like this. I guess I'm not drawing that completely correctly, but you get the idea that all these magnetic field lines are doing something like this over the surface of the planet. And maybe you've never thought about this before, and maybe you think this is wholly insignificant, but I think it's just interesting. It means that if opposites attract with magnets, just like charges, right? North poles want to align to south poles of other magnets. Then that means that your compass needle pointing north is pointing to magnetic south of our planet. Did it really? Okay, great. I didn't know if it, I couldn't remember if it brought that up or not. But yes, it means that what we are pointing towards when we were talking about magnetic north runs along that wall right there in this classroom. So north is going to point that way if you had a compass needle. That means we're pointing towards magnetic south, where Santa lives. Yes. So what we call the North Pole is the magnetic South Pole. And then you can go over, I can't remember where it is. I think it's somewhere over the Southwest Pacific Ocean. There's the, no. It's, of course, it's it's in the North Atlantic. It's called the North Atlantic Anomaly or something like that. It's where we got weird termination of magnetic field lines into the planet at that point. Unfortunately, it's not over the Bermuda Triangle, so it doesn't explain that, but you get the idea. But it's just interesting to me about how, like, I don't know, that hadn't occurred to me. I feel like there was something else that I wanted to say significant in terms of that. But yeah, if you want to go into planetary science, we have an idea of where our Earth's magnetic field comes from, but we don't know yet. Does anybody have a planetary science explanation, or at least the current understanding of it? Right, so it's not causing Earth's rotation, it's because of Earth's rotation, right? So he's right. So we have a very iron-rich core, right? And one of the things that I said before was that moving charged particles generate magnetic fields, and you've got a lot of metal that becomes ionized in the core that is then rotating. And one of the things we're going to talk about is a circular wire. And the magnetic field generated by a circular wire comes out to be more or less the same magnetic field of a bar magnet, which is what you've got right here, right? We're going to come back to this drawing in just a second. Yes?
Is the Earth electromagnetic or just magnetic in general?
So the question was, is Earth magnetic or electromagnetic? What I'm talking about with these blue lines are the magnetic fields. There's electric charge, though, that generates those in our core, a disproportionate amount of charge distribution. But here's the thing that gets back to the heart of your question is, by the end of this unit, you cannot think of electricity and magnetism as being two different things. Electricity and magnetism are just two sides of the same coin. Okay? I know that's not much of an explanation right now, but I think that will kind of come out along the way here.
Is because the magnet spinning, I don't even want to go, but because the magnet spinning, is that why it's perpendicular to rotation?
Yes, so that's going to be what we talk about on Thursday or Tuesday of next week, the Biot-Savart law. The direction of the moving charge is going to be perpendicular to the magnetic field it generates. Okay, so magnetic fields exert a force on moving charged particles according to F equals QV cross B. So charge times velocity times magnetic field strength, where the units of magnetic field are measured in Tesla, not the strange vehicle that drives around autonomously, but the unit Tesla. A Tesla is a Newton per amp meter. And the Tesla is a large unit, so another more common unit of magnetic field strength is the Gauss. A Gauss is 10 to the minus 4 Tesla. If you have a 1 Tesla magnet, there will be issues. If you put two 1 Tesla magnets together, it would be probably beyond the strength in your own arms to pull those two magnets apart. A Tesla is an enormous amount of magnetic field strength. The Earth's magnetic field along the surface of the Earth ranges in the order of 10 to the minus 5 Tesla. So 0.1 Gauss. But force is equal to QV cross B. So let me go back to my set of drawings here. I get let's go with the proton, actually. So this is a proton, and it's got some sort of velocity. Actually, I'm going to do it this way. It's going to have some sort of velocity like this. And let's say that the magnetic field lines, B, look something like this. And we said that force is equal to Q, V, where this right here was V, crossed into B. Now, what I'm trying to show you is that this V, if I project it down onto the magnetic field, right, there's going to be some angle between them. And I've got a bit of the velocity here. We'll call this V parallel. And I've got a bit of this velocity here that is perpendicular. Right? V parallel and V perpendicular. Here's what I'm getting at. What happens, let's just do the one at a time. What happens to the parallel component of the proton's velocity? What happens to the parallel components of the proton's velocity? How does it change? Right? Because force is akin to acceleration, and acceleration is akin to changes in velocity. So how does the parallel component of the velocity of the particle change? What? It doesn't, I'm just assuming this is a uniform magnetic field. So distance away from the field, we're not worried about. We're wholly embedded in this uniform magnetic field. So what happens to the parallel component? It doesn't change, right? Because we're taking the cross product here, and the cross product between two parallel vectors, right? Let's say A crossed into itself, right? Well, any vector crossed into itself is the null vector. It's 0, right? So that means that V parallel is constant. What about V perpendicular? I saw some of you already exercising your right-hand rule. We'll get to that here in a second. But the right-hand rule is going to give us a way to calculate in what direction is the force. So B is going to be to, actually I'm going to start with V. V is going to be down and to the right here. And then I want to turn my palms such that as I curl my fingers, they would point in the direction of the magnetic field. And so at least as I've gotten this drawn out here, your thumb is going to be the direction of the force. The thumb is going to be the direction of the force, and you would get a force here that is out of the page, out of the screen. And so what happens, and what I'm trying to get you to see here, is that what this is going to do, whoops, is you get this nice little helical motion here of your charged particle, where the parallel component of the velocity does not change, but the perpendicular component of the velocity experiences a constant centripetal acceleration, so long as the magnetic field is constant. So, every second we are getting bombarded by the sun, our own planet is getting bombarded by the sun, by trillions upon trillions of cosmic rays, which is just an astrophysicist's fancy way of saying high energy protons. Right? And what happens is those protons are going to have some amount of velocity that is parallel to the magnetic field and some component that is perpendicular to it. And those particles are going to end up getting trapped around our magnetic field lines. And they're going to follow those down here until the magnetic field gets too strong, at which case, and there's an equation you can find or an energy case you can find to solve this, they can bounce back. But some of them are going to come into the Earth's atmosphere up here, where the magnetic field comes into our own planet. What on earth do we observe based on that phenomenon? Aurora Borealis and Aurora Australis. This is where it comes from. You get charged particles get trapped by our magnetic fields and start going into helical motion until they get enough energy and they enter our atmosphere. They interact with the atmosphere, ionize it, and ionized particles, when those ions decay or when they recombine, they're going to give off light. Beautiful greens and blues and reds and pinks. In fact, this last summer, if you went outside and looked, you could see a little bit of the pinkish hue from the aurora from a higher energy solar flare that was aimed right at our planet. Bad stuff. Okay, enough of that. So, in what direction is the magnetic force on the moving positively charged particle? Is it toward the top of the screen, toward the bottom of the screen, to the left, to the right, into or out of the screen? Which one do you guys think? Good. So into the screen is the correct answer here. The first four that we can rule out are top and bottom, left and right. Because of the cross product, our correct answer has to be perpendicular to the velocity. So it can't be up or down, top or bottom. And it has to be perpendicular to the magnetic field, so it can't be left or right. And so you align your middle finger to V, turn your palm towards B, or that is to say, turn your hand such that as you close your fist, your fingers point in the direction of B. So maybe if I use the one here on the board, I align my fingers to V, I turn my hand, my palm, such that as I curl my fingers, they point towards B, and that means into the screen, I get my force. So this would want to bend in towards the screen. Either V would have to be reversed or B would have to be reversed. Either one of them being reversed would give you a velocity or a force out of the screen. Right? If it was reversed, if velocity was down, then I turn my fingers to go down, I rotate them to go to B, and then my force is out towards you guys. If I was still velocity up, but B was going in the opposite direction, then I get a force coming out towards you guys. Aha! What if the charge was negative? Let's practice one more with the positive charge, and then I've got two that are negative. So in what direction is the magnetic force on the moving positively charged particle? Maybe the videos mentioned this last night, maybe they didn't. But if you see a field of X's, you're seeing the back of vectors, the arrows, the fletching, if you will. And so that means that B is going into the board. If you see a field that's dots, you're seeing the tip of the arrow, and that would be coming out of the board. So X's into the board, dots out of the board. If it's X's and O, you've gone back to Valentine's Day, and you're in the wrong discipline altogether. All right. Sorry. Bit of a diversion there. Sorry. The correct answer is towards the top of the screen here. Yes. You get the top of the screen following this explanation. Align your middle finger to V, so to the right. Turn your palm towards B. That would be into the board. You would get a force going to the top of the screen. Yes. Dots would be coming out. Yeah, X's and dots. If it's X's and O's, you have a secret admirer. All right. Now, what if it's negative? So our definition for force was Q times V cross B. So V cross B gives you one piece of it, but then Q is negative. And taking the negative of a vector flips the direction. So take V cross B, just like we've been doing. You'll get a result, but then you have to flip the direction because the charge is negative. So in what direction is it for a negatively charged particle? Then you get for this one, I'll let a few more folks chime in here. You get a force to the left. Everything this electron owns in a box to the left. Align your middle finger to V. Turn your palm towards B, so that would be into the board, palm up, or fingers curling upward. That would give me a force to the right, which is what a quarter of you put. But then because the charge is negative, that means that you have to flip the sign of your force, the direction of your force, which means a force back to the left. Yes, I said up here for a moving negatively charged particle. Not just they, but I told you. All right, last one of these questions, and then we're going to go through a little bit more. In what direction is the magnetic force on the moving negatively charged particle? Again, that would be a velocity out of the screen. Magnetic field to the right is going to be all over the place on this one. All right, someone put to the left, someone put out of the screen, and someone put bears. I don't know. You'd have to ask, who is it, Alec Baldwin? Isn't he the guy on the SNL sketch? Da bears. All right. Correct one here is toward the top of the screen. We can rule out in or out of the screen or left and right based on the directions of the velocity and magnetic field. And you get the top based on V cross B being down, but the negative flipping our sign over, going back up. I'm going to go ahead and tell you guys, this is my favorite exam to give as a professor because I love just pausing from whatever I'm doing and watching all of the people trying to do the right-hand rule, and you're all trying to do it to yourself because you all think you don't look cool, but everybody's doing it. It's all good, right? Yeah, I mean, you could make it look cool and make it look like you're trying to use the Force or something like that from Star Wars. I don't know, but so if moving charged particles experience a force due to magnetic fields, well, current is made up of a bunch of moving charged particles. So currents are going to experience a force as well. And we're already, electrical engineers, starting to get into some of the frustration that you guys have to deal with on your own devices. Because we've got currents, as we're going to show next time, generate magnetic fields. But currents also experience a force due to magnetic fields. And so you get, I don't know, some crazy stuff in terms of force on currents that could be an issue. Not as much as mutual or self-inductance, but certainly not something that is fun to deal with. Considering a current is a series of moving charged particles, the magnetic field exerts a force on the current as well, where you get F is equal to IL cross B. Or if, unfortunately, the wire is not always pointed in one direction, it's just going all over any which direction, we get to do an integral. Woohoo! Yay! I'm so excited. Love integral calculus. Physics is fun with a capital PH. An important note, since there are no isolated magnetic fields, I said we'd talk about this maybe next time or later on. Now is later on. This is actually a good drawing of a bar magnet showing the magnetic field lines traveling all the way through that material. Since there are no isolated magnetic charges, magnetic field lines form complete loops with no beginning nor end. Maybe last question, I think? No. Since the magnetic force is always perpendicular to the velocity, magnetic forces do positive, negative, or zero work. The correct answer is zero. They do no work. Recall from pH 111 that an amount of work is F dot dl, and if the force is perpendicular to the distance, which is it has to be based on the definition of the cross product, then the dot product is going to be zero. If you take the dot product of a cross product, is what this is saying, the answer is always zero, if you're using the same set of vectors. We'll come back to that we'll pick up here on Thursday. So y'all have a great day, and I will see y'all Thursday.